The goal for today is to review partial fractions and get some practice using partial fractions in helping us to solve Laplace transform problems. Now, why do we want to do partial fractions? Well, the whole spirit of partial fractions is pull things apart into smaller, easier to manage pieces. Why do we want to do that? Well, when we look at the kind of things that we actually are able to do with the inverse Laplace transform, there's not that many things. And so in order for us to succeed, we have to make it look like things that we recognize. So we have to pull things apart into smaller, easier to manage pieces. So let's start by taking a look at some basics of partial fractions. So the spirit of partial fractions says we want to pull things apart. Now there's ways you can do it if you don't mind not being correct, but of course, if we're not correct, we won't get points. So here's a simple example, 1 over x squared plus x. And you might say, aha, I see a plus. Well, shouldn't that be 1 over x squared plus 1 over x, right? Right? No, this is not true. That does not work. And see, the issue is a plus downstairs is not a good plus. A plus upstairs, that's a great plus. So what can you do? Well, what you can do is you could say, well, this is really 1 over x times x plus 1. And when you do partial fractions, you say, oh, I want to separate it so it's just something over x plus 1. And it is possible. And it turns out this is 1 over x subtract 1 over x plus 1. Now, how you get there, that's the whole point of what we're about to talk about. So, what's going to happen? Well, we're going to take our denominators and we factor them. And as we factor them, we factor into pieces. Now, in this case, there were 2 pieces, x and x plus 1. In general, we'll have some number of pieces, and they fall more or less into 2 camps. One camp are what we would call linear terms. So something like s minus c, or we might have s minus c to the power. So if we see that downstairs, we say, okay, in terms of the pulling apart, what we're going to have is a bunch of pieces. So s minus c squared, all the way up to s minus c to the power k. And you'll notice we have some unknowns, a1, a2, up through ak. In essence, partial fraction says it can pull apart for the right choices, and you say, okay, let's see what the form is, and then we make the right choices. Very similar to how we did undetermined coefficients. Now, that was one possibility, s minus c. The other possibility is we get something that can't get down to what we would call linear. We get down to what you call irreducible quadratics. In other words, it's a quadratic that doesn't factor any further, or you could say it's a quadratic which would have imaginary roots. So they tend to look like s minus c squared plus b squared. Now, if what you have is irreducible quadratic, the downstairs, okay, again, you work your way up. The only difference is upstairs, there's a little bit extra. So it's something s plus something, all the way up. And so you have that extra term. All right, so what's our procedure? Well, let's grab it here. The whole punchline is we factor our denominator, and then we're going to see we have some unknowns. And those are our a's, b's, and c's, and we have to determine them. And so the only thing left to do is say, okay, let's determine these unknowns. Well, how to do it? There's a couple of ways. The way I always start is I say, look, clear out your denominator. And so you multiply both sides by the denominator of what you started with. And now what you'll get is polynomial equals polynomial. And now you say, okay, great. Once I have polynomial equals polynomial, I can use properties of polynomials. Now, the property I like best is actually number 2 here. It says, look, 2 polynomials agree if they equal each other at all points. So choose wisely. In other words, choose values that make things disappear, make things go to zero, and then you can quickly solve for constants. Another thing you can do is you can say, well, look, two polynomials are the same if and only if their coefficients match. So what you can do is you can expand and you group coefficients and say, okay, compare, s squared over on this to s squared on that, s on here, s there, constant, constant, and you get a system of equations and unknowns, and then you can solve. There is another fun thing you can do, which is very specialized, and that is that it only works if you have a nice power downstairs, or like s minus c to the k. And in that case, you say, derivatives. Two polynomials match if and only if all derivatives match. So you just keep taking derivatives and plug in, life is good. And we'll see an example of all these different techniques as we move along. One thing I want to emphasize, and this is important, and we'll do this a few times, but that is to say, partial fractions is only for the following scenario. It has to be a polynomial upstairs, and it has to be a polynomial downstairs. So if it's not polynomial, do not do partial fractions. Partial fractions is not the right tool yet. You have to do something to get to polynomial over polynomial. And we'll see how to do that. There'll be cases, and we'll talk more about that in the next few lectures. So, all right. One thing you might say is you go back and say, wait a second, there was one other thing that often happened with partial fractions that you haven't mentioned yet, which is usually don't you need to check for long division and maybe do long division? The answer is not for Laplace transforms. For Laplace transforms, there's not going to be any long division. So you don't need to worry about that. So it's great. So we have our plan. We factored the denominator. We then pull things apart and put them into the right form with some unknown numerators. And then we solve for those unknowns. And then we have our partial fraction decomposition. Let's do some examples. So let's find the partial fraction decomposition of 10s cubed minus s squared plus 10s plus 9 all over s squared plus 1, s minus 2, s plus 1. All right, good. Now, in this case, they've been very nice. They already gave us the factoring downstairs. In general, they'll give us something that's either super easy to factor or they'll give it to us already. So, okay, great. Now that we have it, the first thing we want to do is pull it apart in the form, right? So we say, okay, we look at our pieces. We have three pieces. Well, we have a s squared plus 1. All right, so we'll have something there. We have an s minus 2. So we'll have something there. And then we have an s plus 1. And so we'll have something there. All right, now say, okay, those are the right pieces, but what goes upstairs? Well, for the s squared plus 1, that's the irreducible quadratic kind. So that's going to actually have an as plus b. In other words, it's a linear piece. Here, it's a linear, so that's no problem. And c and d. All right, good. Now there is actually sort of a sanity check, which is to say the following. The number of unknowns, so here we have 1, 2, 3, 4 unknowns, A, B, C, D, has to match the degree downstairs. Well, it's 1, 2, 3, 4, degree 4. Okay, so 4 equals 4. If they don't match, you either have put in too many unknowns, and that'll lead you into trouble, or you put in too few unknowns, which will probably get you in even more trouble. And so just have the right number. Practice, practice. And after you do a few of these, it gets easier. As I often say, the first 1,000 are always the hardest, and then after that, it gets a little bit easier. All right, so next step. Well, we're going to be solving for our A, B, C, D, and so we want to clear the denominators. So the way we clear the denominators is you come here on the left-hand side, and you say, all right, let's multiply by this denominator. So we're going to multiply by our s squared plus 1, our s minus 2, and our s plus 1. We're going to multiply both sides. And when we do that, what do we have? Well, we have on the left-hand side, it's just the numerator, 10s cubed minus s squared plus 10s plus 9. On the right-hand side, well, what's going to happen is that you'll get a little bit of cancellation. So for instance, in the first term, the s squared plus 1's cancel. So we're going to get as plus b times s minus 2, s plus 1. And then on the next term, the s minus 2 cancels. So we'll be left with an s squared plus 1 and an s plus 1. And in the last term, well, it's the s plus 1 that cancels. So we'll be left with an s squared plus 1 and an s minus 2. All right. Now, we could expand, but I always like to start with make good choices. So, do we have some good choices that can be made? And I think we have some. So what can we do? Again, when you're looking for a good choice, you say, what's something that makes zeros? So for instance, see this s minus 2? What would make that 0? So in other words, what value of s makes s minus 2 disappear? Well, the answer will not surprise you. It's s equals 2. So we say, all right, well, let's plug in s equals 2. And we'll plug it into both sides. So we have 10 times 2 cubed, that's 80. Oh, that's a big number. Minus 2 squared, so that's minus 4, plus 10 times 2, 20, plus 9. Okay, equals, well, we'll have 2a plus b times 0 times 3. Great, 0 goes away. On the last term, we're going to get d times 5 times 0. Great, goes away. So it's only the middle term. So that equals c, and then we'll have 2 squared plus 1, that's our 5, and then 2 plus 1 is 3. All right, well, let's see. What do we have here? 80 plus 20 is 100, and then 9 minus 4 makes 5, so that makes 105. And then 5 times 3 is 15, so that's 15c. Well, okay, is 105 divisible by 15? Hopefully. And it turns out, yeah, it is. So if you take 105 divided by 15, you end up with 7. There we go. All right, good, good. Progress, wonderful progress. All right, well, one choice. We've already solved for one of our unknowns. See what good choices give you? Just like taking differential equations, another good choice that you've made. Well, let's try another choice, right? Well, s plus 1. What's good there? Minus 1. All right, so we can plug in minus 1. All right, well, 10 times minus 1 cubed, that's minus 10. And then here we have minus 1 squared, so that's minus 1. 10 times minus 1, minus 10, lots of minuses here. And, well, plus 9. Now we're going to get minus a plus b times minus 3 times 0. Aha, 0. See, 0 is a friend. We like 0. Then we have c times 2 times 0. Ah, wonderful. Then we have this last term. Well, what is that? We're going to have d, and then we'll have times 2, and then times minus 3. All right, well, let's see. What do we get? Well, here we have minus 21 plus 9. Minus 21 plus 9 makes minus 12. And then over here, we'll get minus 6 times d. And so our conclusion is d is 2. All right, great. We're halfway. Now, you might say, what do we do next? Well, what can we do? Well, there's a couple things we can do. And I would say, you might say, well, s squared plus 1, what makes that 0? I could do I, and is that a good choice? And it does work, but you have to be careful. So does I work? Yes. You plug it in, and actually it can usually get you 2 for the price of 1. And the way it works is you say, okay, real recognizes real, which is to say, if I plug in a value and I expand, then the real part on the left and the right side have to be equal, and the imaginary part on the left and the right side have to be equal, and that's enough to figure out both A and B at the same time. The trade-off is you have to work with imaginary numbers, and that can be challenging sometimes. So I tend to avoid that. If you're great with working with imaginary numbers, more power to you. So what can we do? Well, notice we're left with A and B that we don't know, because we've already gotten C and D. And A has an S attached to it. So, idea. Let's plug in S equals 0. All right, well, the nice thing about 0 is it's very easy to compute. 0, 0, 0, 9. All right, great. And then we have B, and then minus 2 times 1. Okay. And plus, then we have C, but C is 7. So 7 times 1 times 1, right? 7, 1, 1. Plus D, which is 2, so plus 2. And then we have 1 and minus 2. All right, so if we carefully expand this out, that's minus 2b, 7 minus 4. So 7 minus 4 makes that a plus 3. Well, okay, we can rearrange things. We can move the 3 across and say, all right, well, this is really the same thing as minus 2b is equal to 6, and therefore b is negative 3. And that's it. It's easy as that. Well, not that that's easy, but it's doable, is that right? And now we just have one more. And at this point you're saying, Steve, you've run out of numbers that are nice. That's okay. Now we only need one more. Plug anything in. Where by anything we mean plug something simple in, right? Because we remember, we love ourselves. And because we love ourselves, we're only going to do things that are relatively easy to work with. All right, so we've already plugged in 2, negative 1, and 0. Is there any other nice number that we haven't plugged in yet? 1. We'll choose the 1. All right, so S equals 1. All right, so we'll have 10 minus 1 plus 10 plus 9 equals, okay, over here, we're going to get A times 1 plus B. Well, we don't know what A is, but we do know B. So that's going to be A minus 3. And then we'll have 1 minus 2 is minus 1. And then 1 plus 1 is 2. Then plus C, which is 7. 1 squared plus 1 is 2. 1 plus 1 is 2. And then we'll have D, which is 2. And then 1 squared plus 1 is 2. And 1 minus 2 is minus 1. Okay, so let's see. 10 plus 10 plus 9 is 29. Subtract 1 gives us 28. Great. Then we'll have a minus 2 times A minus 3. So that becomes minus 2A plus 6. 7 times 2 times 2 is 28. And then 2 times 2 minus 1 is minus 4. Well, the 28s cancel. 6 minus 4 is 2. So this says that 2A equals 2, right? because I can move the 2a across, equals 2, or a equals 1. Great. So we've gotten A, B, C, D. We've got everything. All right. And so we're ready. The answer is we just plug these numbers back in. Now you might say, that sounds easy. Because it is. You just plug them back in. But I will tell you, I have seen many students who do this brilliantly up to this point, and then they forget to plug it back in. So just make sure you get everything in. So we're going to have A is 1, so that makes it S. B is minus 3, S minus 3 over S squared plus 1. C is 7. Okay, so plus 7 over S minus 2. And then D is 2, so plus 2 over S plus 1. And that's the answer. See? It's not so bad. It's not scary. It's just practice. Practice, practice, practice. So we're going to do some more practice. That's what's going to happen next. All right, let's keep going. So let's do the following. Find the inverse Laplace of 3s plus 1 over s squared minus 4s plus 3. Well, what's going on? First off, it doesn't quite look like anything on our table, but remember, the goal of the inverse Laplace is to say there's only a few things we can do, and so if it doesn't look like anything on our table, can we make it look like something on our table? Can we use algebra? Well, I think we have a chance. Maybe we could use partial fractions. Just a thought. All right, so let's think about this. 3s plus 1. All right, not much we can do upstairs. But this s squared minus 4s plus 3, does that factor? Yes, it does factor. It factors as s minus 1 times s minus 3. And you can check, right? It's s squared, good. Minus 3s minus s is minus 4s, and then plus 3. All right, great. So now we say, well, let's do partial fractions. We have downstairs, we have two pieces, so we're going to have two terms. One for s minus 1, one for s minus 3. And then upstairs, well, we'll have, since it's a linear piece, an unknown a, and here we'll have an unknown b. A over s minus 1 plus b over s minus 3. All right, well, good. Next step, clear your denominators. So for us, that means multiply s minus 1 times s minus 3. And when we do that, what will we have? 3s plus 1, because we've multiplied by the denominator here, so that's simple. Here, the s minus 1's cancel, so we have that this is a times s minus 3. Here, the s minus 3's cancel, so we're left with a b times s minus 1. And can we make good choices? Well, yeah, we can make good choices. And so what are some good choices? Well, let's plug in 1. 3 times 1 plus 1 is 4. 1 minus 3 is negative 2. And 1 minus 1 is 0, right? We didn't just choose 1 because 1 is a very pretty number. We chose 1 because it made zeros. And 0 is friend. So our conclusion, A is negative 2. All right, how about 3? All right, 3 times 3 plus 1, that's 9 plus 1. That's also known as 10. A times 0, 0. B times 2, right? 3 minus 1 is 2. It's 2b. And so b is 5. So that says, hey, we can actually rewrite this expression. So in other words, you make a negative 2 and you make b 5. Now, how does this help us with the inverse Laplace transform? Well, it says the following. We have that the inverse Laplace of 3s plus 1 over s squared minus 4s plus 3 is the same as the inverse Laplace of minus 2 over s minus 1 plus 5 over s minus, sorry about that, minus 3. But since inverse Laplace is linear, this becomes minus 2 inverse Laplace 1 over s minus 1 and plus 5 inverse Laplace 1 over s minus 3. And then we're like, oh, these are on our table. What are they? Do you remember? Well, of course, we can just look up on our table and we see that there's a rule that says the Laplace transform of e to the ct is 1 over s minus c, which we know translates to saying the inverse Laplace of 1 over s minus c is e to the ct. So this becomes minus 2 e to the t, right? Because here c is 1, and then plus 5 e to the 3t, because c is 3. And there we go. That's the answer. Nice. Good. Good. Well, now we see why partial fractions is a handy tool for inverse Laplace. Okay, well, let's see what else we can do. So let's solve x double prime minus x prime minus 2x is 10 sine of t with some initial conditions. X of 0 equals 10, x prime of 0 equals 9. Now, notice that we are talking about Laplace transforms, so we're definitely going to use Laplace transforms to solve it. We could do this by other means. This is something we could have solved in the first part of the course, but we'd have to do some various things. We'd have to solve the homogeneous part, solve the particular part by undetermined coefficients. We'd have to then find the general form, and then use the initial conditions to solve for constants. Doable, and we just want to do it now with our new tools to say, okay, let's see how the process works. So there's more or less 3 big parts to it, right? There's transform it using Laplace transforms. In other words, we're going to take the Laplace transforms of both sides. Then we're going to solve for x of s, capital X of s, right? And then cleaning that up as well, preparing for the final step, which is to undo Laplace transforms, taking the inverse Laplace. All right, so we have more or less a game plan. So let's start by taking the Laplace transform of both sides. All right, so we have that the Laplace transform, and I'm going to use that, it's nice and linear, x double prime minus the Laplace transform of x prime minus 2 Laplace transform of x is 10 Laplace transform of sine of t. Okay, so we've plugged it into both sides. Now we really aren't done yet because we haven't really pulled out the full machinery. We've got to talk about each part. So let's pull up our formula sheet here. Happen to have it handy. And as we look at it, we say, okay, the sine, that's pretty straightforward. Laplace of x, well, we'll call that capital X of s. And essentially, that's what we're going to be working for, trying to solve. We also have ways to handle Laplace of x prime. That's where we'll use some of our initial conditions. And Laplace of x double prime, where we'll use even more of our initial conditions. And so everything that we need is on our table. Isn't it great to have tables? I think so. So let's see, maybe we can use this for reference here. So x double prime, so that's going to become s squared. I'll write capital X. We often suppress the of s. It's understood. And I'm going to put some parentheses here because I know that parentheses are our friends. And so that is our first term minus Laplace transform of x prime. Okay, so I'm coming here. That'd be s capital X minus x0. Then minus 2. Laplace transform of x is capital X equals 10. And the Laplace transform of sine will be here, since b equals 1, 1 over s squared plus 1. So 10, 1 over s squared plus 1. All right, good. We can put this aside for a few minutes anyways. Say, all right, what comes next? Well, let's plug in what we know. Okay, so we know our initial values, right? Initial values come at the start of Laplace transform problems, not at the end. It's one of the things that makes it a little bit different. So our x at 0 is 10, and our x prime at 0 is 9. All right, and so with that, let's gather. So we'll gather the capital X terms. All right, what do we have? Well, we have an s squared. We have a minus s. And we have a minus 2. Now, it's going to happen that this s squared minus s minus 2 will look an awful lot like these coefficients here. Because it's going to happen. It's just the process. It feels like characteristic polynomials. There's a reason for that. So that's good that it's happening. All right, what else do we have? Well, here we have a minus 10s from that part. Now here we have a minus 9, but over here we're going to get a plus because there's two minuses. That's why we want parentheses to help us remember that this minus distributes through. So a plus 10. So minus 9 plus 10 makes a plus 1. All right, and all of that equals 10 over s squared plus 1. All right, well, good. Progress. Progress, yes, absolutely. And now the goal here is ultimately we're working to solve for x. So we're trying to get that by itself. So let's move the parts not attached to x to the other side. So doing that, we have s squared minus s minus 2 times capital X is equal to 10 over s squared plus 1 plus 10s minus 1. Let's actually put it all together. So I want to make everything over s squared plus 1. So I'm going to take this 10s minus 1 and multiply top and bottom by s squared plus 1 over s squared plus 1. Okay, great. Why are we doing that? Well, to prepare. So we have 10 over s squared plus 1. And then this will also be over s squared plus 1. We have 10s cubed, then plus 10s minus s squared minus 1. Or, if you like, that's the same as 10s cubed minus s squared plus 10s. And 10 minus 1 makes plus 9 over s squared plus 1. All right, good. So we're almost there. We just have to move this term across. Now, before we do, we're going to pause ever so briefly and say, hey, does this s squared minus s minus 2, by any chance, does it factor? Well, we need to have, if it did, we'd want two things that multiply to negative 2, but add to negative 1. So I'm thinking maybe minus 2 plus 1. Does that work? Let's see, s squared, s minus 2s, good, and minus, yeah, it works. Great. So we can divide by that expression. And so at this stage we have the following. We can say that x is equal to 10s cubed minus s squared plus 10s plus 9, all that over our s squared plus 1, our s minus 2, and our s plus 1. Good. All right, so we've solved for x. Are we ready to take Laplace transforms yet? No, because that's definitely not on our table. But what could we do? We could pull it apart. All right, well, that might take a while, right? Because that we'd have to do partial fractions on that, right? Wait a second. This looks familiar. Hold on, let me see. I think I vaguely recall something. Let's see, where we had a 10s cubed, a minus s squared, plus 10s plus 9, s squared plus 1, s minus 2. We already did it! Man, that was so lucky of us. And so, we'll not do it again. We'll just say, look, we know the answer, so we're going to copy this answer down. All right? So, we say, aha, great news for us. This is equal to s minus 3 over s squared plus 1, and then plus 7 over s minus 2, plus 2 over s plus 1, which we can actually go and rewrite just a little bit more. This is s over s squared plus 1, minus 3 times 1 over s squared plus 1, then plus 7 times 1 over s minus 2, and then plus 2 times 1 over s minus minus 1. Now you're probably thinking like, wait, what? Why are you doing this? We're really putting it into very clean form so that when we pull out our table, we can say, look, do things match what's on our table? So for instance, we have an s squared plus 1 downstairs, so we'd like either s or just 1. And then for our s plus or minus things, well, we'd like a 1 upstairs and an s minus something. So that helps us identify how to pull things apart. So this is getting us, everything is just right. So our final step, and this is after some work, right? We spent a fair amount of time on this problem. We can say that little x of t, which is what we're after, that's the inverse Laplace of big X. Well, that is the inverse Laplace of s over s squared plus 1 minus 3 inverse Laplace 1 over s squared plus 1 plus 7 inverse Laplace of 1 over s minus 2 plus 2 inverse Laplace 1 over s minus minus 1, which is, all right, term by term, inverse Laplace of s over s squared plus 1 cosine t minus 3 inverse Laplace of 1 over s squared plus 1 sine t plus 7 inverse Laplace of 1 over s minus 2 e to the 2t plus 2 inverse Laplace of 1 over s minus minus 1, that's e minus t. And done. Finished. Wow, what an answer. What a great answer. But very different feeling from what we would have done from the first part of the course. But we still would end up in the same place. And just a little bit more algebra, right? All right, great. Well, let's keep going. So now let's look at this problem. Solve x triple prime, third order differential equation, plus x double prime minus 6x prime equals 0, with initial conditions x of 0 is 0, and x prime is 0, and x double prime is 0 are both 15. All right, well, we know our process, right? We're going to take Laplace transform. We're going to clean things up, get ready for inverse Laplace, do it, and life is good. So we start by taking the Laplace transform of both sides. So Laplace transform of x triple prime plus Laplace transform of x double prime minus 6 Laplace transform of x prime is equal to the Laplace transform of 0. Now, the Laplace transform of x triple prime is what? Well, it is, we're going to have s cubed x, and then we're going to work our way up. So s squared times x of 0 minus s x prime of 0 minus x double prime of 0. Okay, so that's the first term. Plus the next term, Laplace transform of x double prime, s squared x minus s x of 0 minus x prime of 0 minus 6. Okay, Laplace transform of x prime, s x minus our x of 0, and all that equals the Laplace transform of 0, which is 0. Nice. Okay, well, let's plug in what we know. Well, certainly we can't plug in what we don't know, so it's a good idea to plug in what you know. We know what x of 0 is. So everywhere where we see x of 0, we say good news, that's going to be 0. So that's very helpful. Then x prime and x double prime are both 15. So I say, okay, you're 15, and you're 15, and you're 15 as well. Okay, so what do we have at this stage? Well, we have the following. Let's gather everything with an x attached. So there's 3 terms with x attached. Namely, we get the s cubed plus s squared minus 6s times x. It's always good sanity check just to say, okay, does this look like the characteristic polynomial? If it does, you probably are on the right track. If it doesn't, whoop, double check. All right, now what hasn't gone away? Well, we have here, we have a minus 15s. Okay, so we're going to need that. Here we have a minus 15 and another minus 15, which makes minus 30. And, well, that's all. All right, great. So let's clean it up. Now, the goal, remember, is what are we doing? We're trying to solve for our function capital X. So it's like, okay, so we're after that. So we're going to move our other pieces across and then divide. All right. Well, so we can say the following. We have s cubed plus s squared minus 6s times x is equal to 15s plus 30. Now let's look at this coefficient. And we kind of anticipate that we're going to be heading towards partial fractions. So let's see if we can do some factoring. We might as well do it right now. Let's see, we can do an s, pull it out. That would be s squared plus s minus 6. And okay, let's see. Can we factor that? Well, 2 things multiplied to negative 6 add to positive 1. I think plus 3 and minus 2 might work. Let's check. S squared, that's good. Minus 2s plus 3s. Ooh, nice. And then minus 6. Ah, nice. And so we have the following. We have that this is x is equal to 15s plus 30 divided by s times s plus 3 times s minus 2. Now, we're not ready for inverse Laplace. We got to find a way to rewrite this. So we say, okay, we've already factored the downstairs, so that's good news for us. Yay, us. And we have our 3 pieces, right? And so we say, okay, so we're going to end up with 3 terms. Something over s plus 3, something over s minus 2. So we'll have constant a, b, and a c. And again, number of unknowns, 3 equals the power of the denominator downstairs. Okay, So we're going to have to figure out A, B, and C. Well, let's give ourselves some space and see what we can figure out. Multiplying through by s times s plus 3 times s minus 2, we'll get 15s plus 30 is equal to A times s plus 3 times s minus 2 plus B times s minus, I'm getting ahead of myself. S times s minus 2 plus C times s plus 3. Okay, so again, we've multiplied everything by this denominator, and so no denominator left, 15s plus 30, and then for each term, one piece canceled. All right, well, now make good choices. Yes, make good choices. Okay, well, let's see, what's a good choice? 0. That's a nice choice. So plug in s equals 0. What do we get? Well, 30. Here, we get a times 3 times minus 2. That's minus 6a. Then 0 because of the term s, and 0 because of the term s. So we say, aha, a is negative 5. Well, that's good. Okay, well, how about another good choice? How about 2? Right, because you see 2 minus 2 would be 0. Okay, so we'll plug in 2. 2 times 15 is 30, plus 30 makes 60. Equals A times 5 times 0, gone. B times 2 times 0, gone. C times 2 times 5, right? 2 plus 3 is 5. So that's 60 is 10C. So what does that tell us? It tells us C is 6. Cool. All right, well, any more good choices? Yeah, negative 3. All right, well, negative 45 plus 30 makes negative 15. Okay, negative 3 plus 3 is 0, so that term goes away. Similar, the last term goes away. So what do we have? We have b times minus 3 times minus 5. Okay, minus 3 times minus 5 is positive 15. So that would make 15b. So that says b is negative 1. Okay, great. Well, how does that help us? Well, it helps us because it tells us what happens with our partial fraction decomposition. Namely, we have a, which is negative 5, and I'm going to write this as negative 5, 1 over s. Whoops, a is negative 5, but I was pointing to b. Okay, learn to point to the right thing, right? b is negative 1, so I'm going to write that as minus 1 over s plus 3. And then c is 6, so I'll have 6 over s minus 2. I'm supposed to write the 6 in the front. Well, okay. All right, let's try that one more time. Negative 5, 1 over s, minus 1 over s, and I'm going to write this as minus 3, and then plus 6, 1 over s minus 2. And so that's very clean, very ready to take the inverse Laplace transform. So we're now ready to say that our answer to the differential equation, our solution, it's the inverse Laplace of capital X. Well, we worked it out. That's negative 5 inverse Laplace 1 over s minus inverse Laplace 1 over s minus 3 plus 6 inverse Laplace 1 over s minus 2, which is inverse Laplace of 1 over s, 1. So negative 5. And then we have minus inverse Laplace of s minus 3, e to the minus 3t. And then inverse Laplace 1 over s minus 2 is e to the 2t. And there we go. That's our answer. Nice. Good job. Good job, us. And all right, so now we know how to do these, right? So So we got to just keep practicing. But the procedure should become just sort of manual, right? Like, okay, we know how it's going to go. We start with our differential equation, apply a Laplace transform, clean it up, pull it apart, get ready for inverse Laplace, carry out the inverse Laplace. Life is good. Life is wonderful. So I want to show you something that's fun that you can do when you're downstairs. Looks like s minus something to a power. And it's a wonderful shortcut. Okay, so find the inverse Laplace of s to the fourth minus 3s cubed minus 2s squared plus 5s plus 8 all over s minus 2 to the power 5. Okay, now really the heart of this problem is just, can you do the partial fractions? All right, because we have s minus 2 to a power, what's going to happen? Well, what's going to happen is we're going to march our way along. So we have s to the fourth minus 3s cubed minus 2s squared plus 5s plus 8 over s minus 2 to the fifth. Well, we're going to have something over s minus 2 plus something over s minus 2 squared plus something s minus 2 cubed plus something s minus 2 to the fourth plus something s minus 2 to the fifth. All right, s minus 2 to the fifth, we got to work our way up. And notice A, B, C, D, E, that's 5 unknowns, and we have a fifth degree downstairs. So it's the right number of unknowns. All right, what do we do? Well, we start as we always start. We say, okay, clear out your denominators. So multiply everything by s minus 2 to the fifth. And once you do that, you're going to get to the following. You're going to get s to the fourth minus 3s cubed minus 2s squared plus 5s plus 8 equals a. Now here we have 1 cancel, so that's s minus 2 to the fourth plus b. Here 2 cancels, s minus 2 cubed. C, here 3 cancels, s minus 2 squared plus d. 4 cancels, and then all of them cancel. All right. Whew. Good. Now, at this point, you're like, there's just one choice, right? One choice, and that's 2. And so if you plug in s equals 2, then it's like, all right, I get a number. Okay, great. But then you're out of good choices. And you're like, oh, I still have 4 things left to solve for. Ugh. So here's the fun thing. All right, if 2 polynomials match, and these are 2 polynomials, right? And the whole point is just saying, what are the right choices for the constants so that they do match? Well, if 2 polynomials match, their derivatives match, and their second derivatives match, and their third derivatives match, and so forth and so on. So I'm going to just write down derivatives of both sides. Now, what we're about to do really is super special. Essentially, it has to look like this. You know, s minus something to a power. If it doesn't look like that, don't try this. But if it does, let's use it. Okay, so taking derivatives, 4s cubed minus 9s squared minus 4s plus 5, right? It's not so bad to take derivative of a polynomial. Now, what happens here? We get 4a, s minus 2 cubed, 3b, s minus 2 squared, 2c, s minus 2, d, and then that goes away. Now notice, it's pretty easy to solve for e in the first one. It's pretty easy to solve for d in the second one. Well, it's an idea so nice, we'll do it twice. So 12s squared minus 18s minus 4 is equal to 12a s minus 2 squared plus 6b s minus 2 plus 2c, and that's it. Now we can solve for c. Well, let's do it thrice. Okay, 24s minus 18 is equal to, here we'll have 24a times s minus 2, and then plus 6b. And now, like, great, let's do it one more time. Okay, I love your enthusiasm. Never lose that, never lose that. 24 is equal to 24a. All right, so all these statements are true. And now what we'll do is in each one of them we'll plug in 2. Now, of course, for this one, when you plug in 2, it doesn't matter because there's nothing left. We get a equals 1. Here, when you plug in 2, you'll get 48 minus 18, which is 30. That goes away, so that equals 6b. So that says b is 5. All right, here what do we have? Well, we have 48, 12 times 4, minus 36, that's 12, minus 4 is 8. Okay, 48 minus 36 minus 4. 0, 0, 2c. So 8 equals 2c. So c is 4. All right. Well, we're about up to the point where we actually have to start writing stuff down. Okay, so I'm going to be a little bit careful here with this next one. 4 times 2 cubed, that's 4 times 8, that's 32. 9 times 2 squared, that's 9 times 4, which is 36, minus 8 plus 5. Okay, so what do we have here? We have 32 minus 36 is minus 4, then minus 8 makes minus 12, plus 5 makes minus 7. So minus 7 equals D. Because when you plug in 2, do, do, do. Okay, here, 2 to the 4th, 16. 3 times 2 cubed, 3 times 8, that's 24. 2 times 2 squared, that's 2 times 4, which is 8. 5 times 2 is 10, and then plus 8. Well, at least the 8s, those cancel. That's pretty easy to see. 36, subtract 24. Sorry, not 36, 26. I know how to add. 16 plus 10 is 26. Subtract 24 makes this 2, and that's equal to E. And so we now know our coefficients. We solved for A, B, C, D, E. And we didn't need too much space. Isn't that cool? And so it's sort of like look for patterns. Think about how are polynomials equal? How can you take advantage of that idea? All right, well, okay, so what do we have? We now have, well, okay, let's be careful here. A is 1, so we have 1 over s minus 2. Then we have b, which is 5, plus 5 over s minus 2 squared. C is 4, so that's 4 over s minus 2 cubed. Then here, d is 7, so minus 7 over s minus 2 to the 4th. And then e is 2, so we have a plus 2 over s minus 2 to the 5th. Good, good. All right. Now, we need to think about our rules. So there's a couple rules that are going to come into play here. And our rules that we need to remember, well, the inverse Laplace of n factorial over s to the n plus 1 is t to the power n. We also have that the inverse Laplace of e to the ct f of s is going to be, I'm sorry, I wrote this down wrong. The inverse Laplace of f of s minus c is going to be e to the ct f of t, which when you combine these two together, this becomes that the inverse Laplace of n factorial over s minus c to the power n plus 1 is equal to e to the ct t to the n. All right, so when we go through and look at this, here we have a power, this is the same as n equals 0, and right, s minus 2 to the 0 plus 1. And we say, okay, so we want a 0 factorial upstairs. Okay, good, 0 factorial is 1. So this is good as is. So this is 1 over s minus 2. Here we have s minus 2 squared. That's 1 plus 1. So what do we want upstairs? A 1 factorial. We have right now 5. Well, 1 factorial is just 1. So all right, this says 5 times 1 over s minus 2 squared. Now we come to the next term, s minus 2 cubed. Well, for s minus 2 cubed, what do we want? Well, that's 2 plus 1. So upstairs we want 2 factorial. Well, 2 factorial is 2. We have a 4. So we'll write this as 2 times 2 over s minus 2 cubed. Now we come to the next term, 4. So s minus 2 to the 4th, well, I'm pointing here, but you know, the same thing. And so what do we have? Well, this would be n equals 3. Okay, so what do we want? We want 3 factorial upstairs, which is 6. We don't have 6, we have 7. So what can we do? Well, what we can do is we can pull out 7 over 6 and then put a 6 upstairs. And so then we're good to go. Now the last term, s minus 2 to the 5th, well, what do we want? We want to have, that's n plus 1, so that's n equals 4. We want 4 factorial, which is 24. So we want a 24 upstairs. Well, what do we have? Currently we have 2, so to get there, well, 24 to 2 means multiply by 1/12. All right, so now the key is take the inverse Laplace of that expression. And if you do that, you get the following. Namely, you're going to get e to the 2t. Here, you'll get 5t e to the 2t plus 2t squared e to the 2t minus 7/6 t cubed e to the 2t plus 1/12 t to the 4th e to the 2t. And that is the answer. What? Cool, right? All right, good. Whew. Well, since we have a little bit of time, one more. For our final problem, let's use Laplace transforms to find xs, which is the Laplace transform of x at t, and ys, which is the Laplace transform of y at t, where x is 0 equals y is 0 equals 0, and x prime 0 equals y prime 0 equals minus 1. And we have x double prime plus 2x plus 4y equals 0, y double prime plus x plus 2y equals 0. Now you might be thinking like, whoa, hold on, this feels like systems and elimination. It is. So what we want to do is just talk about like, how can you talk about the systems type problems using Laplace transforms? Does it even make sense? And well, hopefully we'll convince you the answer is yes, and we'll get there, right? So let's just think about the process. Now the good news is we don't have to fully solve the differential equation. We actually could, and it's a fun exercise, and I'll leave it to you to do. We just have to find the Laplace transforms of x and y. Now the way we're not going to do it is try to say, oh, let's set up a system for just x or just for y. One of the issues is, even if we could do that, how do we get the right initial conditions? That's tricky. So we're going to avoid that. So what will we do? Well, let's just channel the process. The process says start by taking the Laplace transform of both sides. Okay, great. And in this case, we'll do it for each equation. So we have from the first equation, Laplace transform of x double prime plus 2 Laplace transform of x plus 4 Laplace transform of y is equal to 0. Now, the first piece here, this becomes s squared x minus s x0 minus x prime of 0. And then these other pieces, well, that'll be 2x and 4y. Okay. And, all right, well, let's clean this up. We know x of 0 is 0. Okay, well, that's helpful. So this part here is 0, and x prime is 0. Well, we know that's negative 1. All right, well, we can now clean this up and say, all right, if we group, we have s squared and 2, so we can write this as s squared plus 2x. Then we have 4y, and then here, this plus 1, we can move across as a minus 1. All right, that's from the first equation. And you're probably thinking like, this is feeling really familiar. I hope so. I hope it does, because it should. Second equation, we have Laplace transform y double prime plus Laplace transform of x plus 2 Laplace transform of y is equal to 0. When we said 0 here, that's really the Laplace transform of 0, but that is 0, so that's okay. We didn't lie. So that's s squared y minus s y0 minus y prime of 0 plus, okay, capital X plus 2y, capital Y, equals 0. But again, we know y of 0 is 0, and y prime is 0 is negative 1. All right, so this becomes what? Well, we have an x, so I'm going to write the x term first, and then we have s squared plus 2y, right? S squared plus 2y, and then that's going to equal negative 1. All right, well, great. So we now get the following. We really have a system of two equations, right? We have our s squared plus 2 capital X plus 4y equals minus 1, and our 1 times capital X plus s squared plus 2 capital Y equals minus 1. Or in matrix form, s squared plus 2, 4, 1, s squared plus 2 times xy equals minus 1 minus 1. Now, what does this feel like? Come on, say it. Kramer's rule. Yes, it's Kramer's rule. So we're going to do that. All right, Kramer's rule. Kramer's rule. Okay, so here we go. Let's suppose we want to solve for x. So then x is what? Well, it's a ratio. And it's the following ratio. What you do is downstairs, it's the determinant of these coefficients. So s squared plus 2, 1, 4, s squared plus 2. We'll figure out what that is. Upstairs, you say, okay, similar, but I replace the x column by minus 1s. So minus 1, and 4 s squared plus 2. Okay, so upstairs we have the following. Minus s squared plus 2, right? Subtract minus 4. right? Okay, downstairs, we'll get s squared plus 2 squared, subtract 4. All right. Well, that makes it here, minus minus 4 makes a plus 4. And then, so we have a minus s squared and minus, actually plus 2, right? Because it's minus 2 plus 4. And then downstairs, okay, well, let's do a little bit of work. And we have the following. That's s to the 4th plus 4s squared plus 4 minus 4. All right, so you expand the first term. The 4's cancel. And you can even pull out an s squared. And so this becomes an s squared times s squared plus 4. All right, and that's x. Good, because that's what we're after. We're after finding x. And note, this is something that we could carry all the way to the end. And so, like I said, it's possible for us to solve, but for right now, we're just getting capital X and capital Y. Okay, similar, I'll work up here in this space because I have it. How do you find capital Y? Well, capital Y is going to be, again, you have same determinant downstairs, which is from your coefficients. Now upstairs, you're going to replace the y column. So it'll be s squared plus 2, and then a 1, and a minus 1 minus 1. Now, we will have minus s squared plus 2, and then we're going to subtract minus 1. And downstairs, well, we don't have to repeat the work. It's the same expression. So it's still s squared plus 4. And if we clean this up, we'll have a minus s squared. Here we'll have minus 2 plus 1. Minus 2 plus 1 makes minus 1 over s squared times s squared plus 4. And there's our y. There we go. All right, so we can use Laplace transform to solve systems, just like we can do it. See how versatile this technique is? Wow, it has 1,000,001 uses. And we just got to get used to, doing it once, right? Practice, practice, practice. You can do this. I believe in you. And we'll see you again soon. Bye.